In the last section, we discussed nucleophilic substitution reactions, where a halide, which is a leaving group, is replaced by a nucleophile such as hydroxide. Hydroxide may also serve as a base that can react with a hydrogen that is neighboring to the leaving group. When this hydrogen is deprotonated and the leaving group leaves, the molecule forms a double bond. Okay, so this reaction is called elimination reactions. Okay, because this molecule eliminates a small molecule, hydrogen and bromine, so hydrogen bromide. So the elimination reaction is an alternative pathway to substitution reaction. It is opposite to the addition. Addition is when you add small molecule, okay, to this double bond. And here you eliminate it. Okay, it generates alkene and can compete with substitution reactions and decrease the SN1 reaction yield. Let's look at some elimination reactions. Here is 2-bromobutane under basic condition, and this is sodium ethoxide. Okay, I hope at this point you are familiar with bases and the nucleophiles. For example, you know hydroxy, that's a strong base, and also a strong nucleophile. Strong base because it wants to add a hydrogen to form water. Okay, so usually strong base is also a strong nucleophile. Similarly, methoxy. All right, that's just like hydroxy, a strong base because it wants to add a hydrogen to form ethanol or methanol. So HCH3. So that's methanol. Similarly, this is ethoxide. Ethoxide is a strong base. All right, it wants to add a hydrogen to make ethanol, CH3, CH2OH. That's ethanol or alcohol. All right, so as a base, it will react with a hydrogen adjacent to this carbon-bromine bond, not this hydrogen, because the hydrogen directly attached to the carbon-bromine bond. Okay, that hydrogen, if you remove it, it cannot lead to a product. All right, it cannot lead to a stable product. So the choice to react the hydrogen is either this hydrogen that neighboring to it, all right, goes here, or this hydrogen, all right, so that adjacent to the carbon-bromine bond, and that will make a double bond between the two carbons. So here can make a double bond, or this make a double bond. So these are the two possible products. So this product comes from this hydrogen. When you remove this hydrogen, it forms a double bond. And if you remove one of this hydrogen, that's the double bond. All right. So when the also bromine leave. All right. So you make a mixture. It turns out that this first product is the major product. That's 81%. All right. Now there's a rule called the Zester's rule, which says in elimination of hydrogen chloride or bromide from an alkyl halide, the more highly substituted alkene product predominates. So when you count the substituents in a double bond, okay, you look at the double bond. So this is the double bond, and hydrogen is not counted as a substituent. So you ignore hydrogen, and you'll find this is one as substituent, and this is another substituent. So this is called a di-substituted. Okay, so this is a di-substituted. Now what about this double bond? Now this double bond, again, you ignore hydrogen and you want a alkyl group there. So that's mono. All right. So this is highly substituted alkene, and that's the major product. Okay. Let's look at another example. So 2-bromo 2-methylbutane. Again, you use a strong base. Okay. At ethoxide, and so the possible hydrogen to remove is either this hydrogen, or this hydrogen, or this hydrogen. Now these two give you the same product. So you have two possible products. So this double bonds comes from when you remove this hydrogen and the leaving group leave. That's the product. And if you remove one of these hydrogens, and that is the product. So again, what is the substituents? So for this double bond, you have one substituent, two substituents, three. So that's a tri-substitute alkene. And this one, double bond, ignore hydrogen, it's a 1 and 2. So that's di. And therefore, this is the highly substituted alkene, and it's predominant 70%, okay, instead of 30%, even though this one comes from more hydrogen, so 6 hydrogen. So statistically, this should give you product if they are equally important. All right, but the product show it's the highly substituted product. All right, will be the predominant product. Practice. What product would you expect from the following reaction? Okay, note that this is potassium hydroxide. That's a strong base. So reaction is probably a elimination reaction. Elimination reaction will eliminate a hydrogen adjacent to the carbon halogen bond. So this is a carbon halogen bond, and you remove a hydrogen. So where are the hydrogens? Okay, an obvious one is this hydrogen. So let's draw more clearly. So this is carbon. All right. So if you remove this hydrogen and also leaving group leave, then a double bond will be here. Okay, so that's one possibility. All right. Now what else? In line bond structure, although we omit to writing carbon hydrogen, but you should be able to identify them. So you should know there's a carbon here, and because carbon has 4 bonds, so you should have 2 hydrogens. Okay. Similarly, there's a carbon here that has 2 hydrogens. So it's possible it eliminate one of this hydrogen, and then leaving group leave, and then you get a double bond here. All right. Now, if you eliminate this hydrogen with chlorine, then double bond here, that gives you the same product. So basically, there are 3 types of hydrogen to remove, but only 2 possible products. Okay. So this product comes from either this hydrogen or this hydrogen. They are symmetric. All right. That gives you this product. If you remove this hydrogen, that's the product. Okay, so which one predominate? We'll look at the substituents. For this double bond, ignore hydrogen, so 1 substituent, 2 substituents, says that's a di-substituents. And this double bond, okay, you have 1, 2, 3, so that's a tri. And therefore, that's the major product. Elimination reaction undergoes several types of mechanisms. One is E1. So E1 is similar to SN1 in that first the substrate leaving group leave forms a carbon cation. So that's similar to SN1. And then the second step, instead of the nucleophile attack carbon cation, it's the base that attack the hydrogen adjacent to the carbon cation and forms a double bond. So that's E1. Now E2 is analogous to SN2. So instead of a nucleophile attack carbon on the back directly, okay, from the halide, here is the base directly attack the hydrogen adjacent to the carbon halide, and the leaving group leave simultaneously give you the product. So we'll see more in detail. Let's compare elimination reaction mechanisms. In E2 elimination, a strong base such as hydroxide attack hydrogen that is adjacent to carbon-halogen bond. The carbon-hydrogen bond break. The 2 electron goes to the carbon-carbon, forms a double bond. At the same time, carbon-halogen bond break, leaving group leave, forms a halide. All this happens simultaneously in a single step, okay, through a transition state, no intermediate. And because the reaction involves 2 reagents, the nuclear base, strong base, and the substrate or alkyl halide, and therefore the reaction is a second order reaction. So K, A, and B. Okay, and that's why it's called E2 elimination. And this is analogous to SN2 reaction, where a strong nucleophile attack the carbon on the back of the halide, and the leaving group leave. So again, it's a single step. Everything happens simultaneously through a transition state, second order reaction, and that's why it's called SN2 reaction. Now in E1 elimination reaction, this reaction undergo 2 steps. First step, alkyl halide carbon halogen bond break, so leaving group leave forms carbon cation, and this step is the same as in SN1 reaction. It also forms carbon cation. Now in SN1 reaction, the second step is a nucleophile attack this carbon cation, forms the substituted product. But in E1 elimination is a base that attack the hydrogen adjacent to the carbon cation, and the 2 electrons of carbon hydrogen goes to the carbon carbon, forms the double bond. All right, so this reaction involves 2 steps. The first step is forming the carbon cation, and because forming carbon cation needs high energy, so this step is slower step. All right, and therefore it's rate determining, or the overall reaction rate is determined by the first step to forming carbon cation. And the reaction, because the first step only involves 1 reagent, and that's the alkyl halide, so the reaction is the first order. So only K, let's say this is B. So only first order reaction, and that's why it's called the E1 elimination. Just like SN1, the first step also forming carbon cation and only involves reagent alkyl halide. So SN1 reaction. All right. Now because the first step forms carbon cation is the slowest step, and the second step is fast, so the base is not very important. Usually you use weak base such as water. All right. So these two, E1 resembles SN1, E2 resembles SN2. Both are most common elimination reaction mechanism. Now there's one that is not very common, which is called E1CB reaction. So in E1CB reaction, a base attack hydrogen first. Okay, attack the hydrogen at the adjacent carbon-hydrogen bond, and this will give you a carbanion. So 2 electrons here forms carbanion. So that's the first step. So it's also 2 steps. First step forms carbanion instead of carbon cation. Carbon cation. So here is a carbanion, and then the base of the 2 electrons of carbanion move to carbon-carbon, between carbon-carbon forms the double bond. Now because carbanion, the 2 electrons negative charge, extremely unstable, so this step is very hard to form. That's why it's not common. All right, unless, okay, in the molecule you have an electron withdrawing group to stabilize the carbanion. So later you will see some examples. For example, you may see a a electron withdrawing group. You will see some examples that can stabilize these 2 electrons. Then that will be E1CB reaction. We have already seen some bases, but here let's go over some of the strong bases. Okay, we start with water. So water is a very weak acid. So pK is 15.7. The smaller the pKa, the better the acid. So this is pK is 15. So that's a weak acid. The conjugated base then is a strong base. Okay, weak acid, strong base. Okay, so when you see hydroxide, you know it's a strong base. So you can see sodium hydroxide, potassium hydroxide. So these are all strong base. All right. Similarly, a methanol, which has, so this is alcohol, the simplest alcohol, pKa 16. So that's comparable to water, and therefore the base is also comparable, strong base. So that's methoxide. Now, ethanol, alcohol, but one more carbon, so very weak acid, comparable. So ethoxide, you already seen this before, it's a strong base. So hydroxide strong base, methoxide, ethoxide. So in the future, when you see C2H5O potassium, and that is actually methoxide. That's a very strong base. Okay. Now here, amine, okay, it's ammonia. The pK is 36. So a large pKa means a very weak acid. So this is a weaker acid than water. All right. So the base, conjugate base, when you deprotonate, it becomes even stronger base. So this is among all these bases, NH2, that's amide, is the most strong base. Okay. It desperately wants to get a proton. Now, we already know that base usually parallel to the nucleophile. So a strong base are usually strong nucleophile. These are all strong nucleophile that can attack positive charged carbon. However, these bases, okay, when they participate in the reaction, they can do both, but elimination, in other words, serve as a base, is usually outweigh the substitution reaction. In other words, they prefer as a base instead of a nucleophile. By the way, in neutral water molecule, it has lone pair electrons. So lone pair electron can donate to a proton, and therefore this is also water itself is a base, but it's a weak base. Okay, neutral water molecule is a weak base. Similarly, methanol is also a weak base. Ethanol, weak base. Ammonia, 2 electrons, and this is a better base. It's a moderate base, but these are very strong base, and this is the most strong base. Here shows more bases. The first one is called DBU. The nitrogen has a lone pair electron. And the second one is LDA. So lithium diisopropylamide. The nitrogen has a negative charge. It has 2 lone pair electrons. So it's a much stronger base. And the last one is T-butoxide. Lithium tertiary butoxide. Oxygen has 3 lone pair electrons with a negative charge. So it's a good base also. Now the important feature of all these bases is that they are crowded. So for example, the second one, you have the diisopropyl. So this one has a CH3, so you have carbon, hydrogen, all right? So it's very crowded, and this one CH3, CH3. So the lone pair electron of the nitrogen is covered by all these carbon-hydrogen bonds, and therefore it's called sterically hindered. Okay, similar for the first one. Note that this is a carbon, you have hydrogen here, so the 2 lone pair electron, the lone pair electron is also covered by these hydrogens and these carbon and nitrogen carbon bonds, and therefore they are sterically hindered bases. Okay, they are strong, but they are sterically hindered. So what's the consequence? The consequence is they can still react with proton because proton is small. So if you come a proton, all right? The lone pair electron can react, but it cannot react with the carbon cation because this is bigger and the lone pair electrons are shielded by the carbon hydrogens, okay? And therefore, they participate in elimination reactions, particularly E2 elimination, but not nucleophilic substitution, okay? No SN2, no SN1, okay? So when you see this basis, DBU, LDA, T-butoxide, all right, think about E2 elimination. Let's look at E2 elimination in more detail. So in E2 elimination, a strong base such as hydroxide, methoxide are needed. The strong base attack hydrogen, the carbon-hydrogen bond break goes to carbon-carbon, and the carbon-halide bond break all happens simultaneously through a transition state, forms the product. Okay, this is similar to SN2 reaction, where a nucleophile attack the carbon and the carbon halide bond break simultaneously through a transition state. Okay, this important feature, all right, they are similar in that nucleophile attack the carbon on the back of the halide in SN2 reaction. All right. Similarly, in E2 elimination, the base attack hydrogen also on the back of the carbon halide bond. So carbon hydrogen bond, carbon halide bond is in 180 degree. Okay, if you have a carbon hydrogen bond in the same phase of a carbon halide bond, at E2 elimination cannot happen. So you can't deproton this hydrogen to form a pi bond unless the molecule can rotate so that this hydrogen goes to the back, all right, and then E2 elimination can happen. Now, SN2 E2 reaction also have important differences. So in SN2 reaction, because nucleophile attack the carbon on the back of the hydrogen, so the steric effect of the carbon is important. A primary carbon is the best, all right, and then secondary. Tertiary cannot happen because the carbon is so crowded. The nucleophile cannot attack the carbon. But in E2 elimination, the base is not attack carbon but hydrogen, all right, and therefore it turns out that the tertiary is very good for E2 elimination because in tertiary carbon, the carbon attached to another carbon which has more hydrogen. So if you have a carbon chlorine in a tertiary, you may have carbon here, hydrogen, hydrogen. This is another carbon, hydrogen. So it's these hydrogens that will be deprotonated. So in tertiary, you may have more hydrogens that can be deprotonated and reaction goes fast, right? So that's the E2 elimination. Tertiary is preferred, and then secondary alkyl halide. Okay, if it's primary, then although E2 can happen, but it prefers SN2 because now the primary carbon is exposed for the nucleophile to attack. Here shows the geometry for the E2 elimination. When the hydrogen, carbon halide is 180 degree, okay, it's called anti-periplanar geometry. So this is a Newman projection, hydrogen, chlorine, 180 degree, and E2 elimination can happen. So you deprotonate this hydrogen, leaving group leave, and that will form a double bond. Okay. Now when the hydrogen and the chlorine or halide in the same side, okay, as shown in this Newman projection, and that's called the syn periplanar geometry. And in this geometry, E2 elimination cannot happen. All right. Practice. What's wrong with the following reaction? It's an E2 elimination, and this is the base. All right, it attacks this hydrogen, and carbon-hydrogen bond break goes to carbon-carbon, and the leaving group is here to leave and forms a double bond. All right, that is predicted product where bromine on the right side, phenyl on the left side. So what's wrong? Okay, so the problem is the hydrogen here that is deprotonated and the leaving group, they are on the same side. Now the requirements for E2 elimination is that they must be 180 degree. Okay, so it's called anti-periplanar structure. In order for that to happen, you must rotate this carbon-carbon bond so that this hydrogen goes to the top. All right, so here is the structure that after you rotate, the hydrogen goes on the top, and then this phenyl goes to the right side, and the bromine goes to the left side. And now this hydrogen and the bromine are anti-periplanar structure. All right, and then hydroxide deprotonate, leaving group leave, give you the final product. But you can see here, the final product has a geometry that is phenyl on the right side after rotate, bromine on the left side, and that is different from what this question is given. And therefore, that's the correct answer. It's a Z conformation. If we have a mixture of tertiary alkyl halides, such as this one, with in water ethanol, that's a weak acid and weak base. So the tertiary alkyl halide, first carbon-chlorine bond break give you a carbon cation, and then the water solvent may serve as a nucleophile that can attack this carbon, forms an alcohol, and that is SN1 reaction. However, water may also serve as a base that deprotonate the hydrogens, and that give you alkene, and that is a E1 elimination reaction. So if you have a tertiary alkyl halide in weak acid base, SN1, E1 always compete with each other, give a mixture. In summary, elimination reaction undergo several mechanisms. The E1 elimination mechanism resembles SN1 reaction. It happens in two steps. The first step forms a carbon cation, which is a rate determining step. The reaction is a first order reaction. Tertiary substrate, product solution is preferred. Zasser's rule is always followed, which means the highly substituted alkene is the major product. In this reaction, a weak base is usually used. In E2 elimination reaction, the mechanism resembles SN2 reaction. The reaction takes place in single-step anti-periplanar transition state. The hydrogen that is deprotonated and the leaving group must be in 180 degree. The reaction follows second-order kinetics. Secondary or tertiary substrate, strong base in polar aprotic solvent is preferred. Now this is in contrast to SN2 reaction where tertiary substrate cannot happen, but in E2 tertiary substrate is preferred because the reaction involves hydrogen instead of carbon. Now because of the anti-periplanar transition state, sometimes Zasser's rule is violated because the most highly substituted alkene sometimes requires the hydrogen and the alkyl halide to be in the same side, which is against the requirements, anti-periplanar requirements. The E1CB reaction mechanism is the least common mechanism in elimination reaction. This happens in two steps. First step forms carbanion. Because carbanion is very unstable, so the molecules usually contains an electron withdrawing group to stabilize the intermediate. So far we have seen that SN1, SN2, E1, E2, they compete with each other. So how do you know which one predominate in a particular condition? Now this guideline may help you in some degree. So first you look at the base. If the base is the sterically hindered strong base, okay, such as this one, okay, so we introduced this in the beginning of this lecture. If you forget, go back to look at it. All right. So this base prefers E2 elimination because they are strong. So they attack hydrogens, all right, directly. All right. However, they are hindered. They cannot participate in SN2 reaction. Okay. That's why whenever you see these bases, then that's E2 elimination. Next, if the bases are very strong, such as hydroxide, methoxide, ethoxide, and also amide, so those are very strong bases. Okay, these bases are so strong, they always participate in E2 elimination. Okay, E2 for tertiary, even for secondary, they are E2 elimination, unless it's primary. So if it's primary, the carbon is so exposed for attack that SN2 may becomes important, but E2 still participate in some degree. Okay, that's for these hydroxide bases, hydroxide, methoxide, E2 eliminations. Unless primary, then SN2 is the major product. Now, if the reactant is bromide iodide, now these are not bases. Okay, they don't like hydrogens. Instead, they like to attack carbons, so carbanions. So they are called nucleophile. They are strong, they are heavier, larger size, negative charge. So they are strong nucleophiles. Strong nucleophiles will participate in SN2 reaction. Okay, they attack carbon directly. All right, so particularly for primary, even for secondary, SN2 predominate, unless it's tertiary. If it's tertiary, then you cannot attack the carbon. All right, so it has to undergo SN1 reaction. SN1 reaction is when the leaving group leave first forms carbon cation. So that's for tertiary. All right, otherwise it's always SN2 reaction predominant for these strong nucleophiles. Now, what if it's water neutral, okay, molecules? These are weak nucleophile, weak base. Okay, for this one, then if its substrate is tertiary, then the reaction is SN1 and E1 compete with each other. You can form alkene, you can form substitute compound by SN1, E1 for tertiary. Now, what if it's primary or secondary? So if primary, secondary, then these primary, secondary cannot form stable carbon cation. So only reaction is SN2, E2, but these are so weak, they cannot attack, and therefore the reaction is too slow, all right, insignificant. Practice, predict the product. So for A, okay, you should recognize this is a primary, actually it's a methyl iodide, the smallest alkyl halide. So SN2 is preferred. And then this is a good nucleophile, okay, positive, negative. So negative charged nucleophile. And therefore, this must be SN2 reaction. So SN2 reaction, this attack carbon, leaving group leave, and the product is methyl nitrate. All right. Now in B, that's a primary alkyl halide, and again prefers SN2 reaction. Now E2 may also happen. So let's look at the base. Okay, E2. Now this is a strong base, methoxide. All right. So this base prefers E2. Okay, unless it's primary. All right. If it's primary, then SN2. So this is a primary. So probably SN2 reaction. So here is a primary, low temperature, good nucleophile or base, the reaction should be SN2, and the product is replace bromine by methoxide. Now in the last question, the substrate is the same, primary, but the base is a strong sterically hindered base. Sterically hindered base cannot happen SN2. Okay, SN2 cannot happen. Only possible is E2. So E2 is take hydrogen away from this one, leaving group leave, forms a double bond here. In these two questions, both substrates are tertiary. Okay, the difference is the first one here is a strong sterically hindered base. So this base only happen in E2 elimination. So E2 take hydrogen away from the carbon adjacent to the carbon. So here that's one hydrogen. If you take this hydrogen away, double bond is here, or take a hydrogen from here and you get a double bond here. So you have two products. So it's an E2 elimination, two products. All right. Now which one predominate? The one is highly substituted. So this one is disubstituted, and this one is tri. So this will be the major product. Okay, next one. Now water is a very weak base. Okay, very weak base, very weak nucleophile, and it's a tertiary. So weak nucleophile, weak base cannot participate in E2 elimination or SN2, and therefore must be SN1E1. So this will leave, forms a carbon cation, and then the water will attack here. That's SN1, all right. And E1 is when, SN1, yes, E1 is this take water or hydrogen and forms double bond. But this temperature is low. Low temperature favors substitution. High temperature favors elimination. So the product should be SN1 reaction, and is a substitution reaction. And E1, if you increase temperature, then elimination will be the major product. In this question, both substrates are secondary. Okay, so for A, this is a strong nucleophile, non-basic. Okay, this is important to recognize, is a strong nucleophile. Okay, non-basic. And therefore, it's SN2 reaction. So SN2 reaction, it will attack here, leaving group leave. All right, that's the product. Now in the second question, and this you should recognize is ethoxide. That's a strong base. All right, so even though it's also a nucleophile, but it prefers elimination unless it's primary. But this is secondary, so it will take a hydrogen. So this hydrogen away, give you the product. All right, so that's the product. Now you may also take a hydrogen here, but this double bond is not highly substituted. So this one should be the major product. In this question, it's again the substrate is a secondary. And here is a very weak base, very weak nucleophile. In fact, it's a carboxylic acid. So it's a very weak base or nucleophile. And therefore, it cannot participate in SN2 or E2. They cannot happen. So only thing can happen is SN1 or E1. So the first step is leaving group leave, forms a carbon cation, and then nucleophile attack. All right, that give you SN1 reaction. So that's the SN1 product. Now it may participate in E1 a little bit, small amount, take hydrogen away, give you a double bond here. Here are some problems in the textbook you need to work on. Problems 15, 16, 17, 18, skip 19, go to 20. If you have time, work on additional problems 27, 28, 29, 30, 50, 51, 52.